Hi everyone, my name is Xingwei Wang, a professor from Electrical and Computer Engineering Department at UMass Lowell. I'm also the PI of this Project 1.5, Distributed Sensing Textile for Bridge Monitoring. Our co-PI is Professor Ziyang Yu from Civil Engineering. This project also supported a few graduate students. Thank you for their contribution. My research interests have been optical fiber sensors. We have designed and developed a few different optical fiber sensors for strain, pressure, acoustics, corrosion monitoring for different applications. Professor Xiang Yu is an expert in remote sensing and also structural health monitoring. In today's talk, we would like to focus on how to apply the optical fiber sensing system to monitor the bridge structural health monitoring. First, we'll talk about why this project is so important. And then we will explain the principle of this fiber sensing textile and how it was developed. And then we will talk about one of our field tests on Salmon Fall River Bridge in New Hampshire. And finally is our conclusion. As we all know that structural health monitoring is very important, that it could avoid the occurrence of the disasters. However, still there are a lot of challenges in current structural health monitoring approaches. For example, how can we monitor large-scale structures? How can we install large numbers of isolated sensors and save the cost for the installation and monitor and collect the data? I think fiber optic sensors could provide a practical solution to some of these problems. Fiber optic sensors have their advantages, including immunity to electromagnetic interference. They can survive in harsh environments, for example, very high temperature up to 600 degrees C, and it can also relay the optical signals over kilometers long. For example, our BOTDR system can monitor the signals over 80 kilometers long. So what is BOTDR? BOTDR is Brilliant Optical Time Domain Reflectometer. So as seen in this figure 1, is a pulse of laser is shined into this fiber, and the light will be scattered and reflected back to the interrogation system. The photon will be backscattered, and this optical frequency of this backscattered light will be up or down shifted from the incident light by the Doppler effect. This frequency shift actually depends on the environment, the temperature, and also the strain applied on this fiber. So therefore, if we can keep monitoring this optical frequency shift, we can know what is the strain distribution along this fiber. So this is the beauty of this system. Instead of providing us the point information, no matter temperature or strain information on each sensing location, instead it can give us a distribution of this strain or temperature mapping all over wherever the fiber sensor is installed. Now, how we make this sensing textile? Collaborative with Xingwei, we embed 2 optical fibers in the sensing textile using the embroidery machine. So this video shows how this embroidery machine is working when embedding the fiber into the textile. In this design, we use 2 kinds of fiber. One is a single-mode fiber for the strain data collection, and the multiple fiber, indicated as this orange color, is used for the temperature monitoring by the DTS. We could design different patterns in the future based on different application environments. After calibration of the sensing textile in our lab, we conducted the field test in Salmon Fall River Bridge, New Hampshire. This bridge is a lattice dash truss bridge with a main span of 102 feet. We installed this fiber sensing textile underneath this bridge. Professor Yu will talk about the details about this installation process.
Thank you, Xingwei. This bridge instrumentation was carried out in collaboration with American Railway Engineers Corp. They supplied a underbridge inspection lift, as seen in the picture, to help us to install the sensing textiles that our students were preparing on site. Before the installation of sensing textiles on a corroded steel bridge, the first thing we had to do is to prepare the surface to ensure the perfect bonding between the sensing textile and the bridge. Engineers from ARE Corp first used the lift and the grinder to remove the surface rust. After the preliminary grinding of the corroded steel surface, they further used acetone to wash out the remaining rust on the surface of steel girders. In this instrumentation, the grinding and the cleaning part took about 1.5 hours. Once the surface has been prepared, the engineers from the ARE Corp also use an epoxy to bound the stencing textiles onto the bottom flange of a steel girder. Showing here, you can see that the stencing textiles were temporarily held onto the steel girder by strong magnets to make sure that the stencing textiles would not fall out of this steel girder before epoxy was dried. Right after the installation, we also tested the quality of the signal to make sure that the signal strength inside the optical fibers was acceptable.
Here is the experimental result. As you can see that the x-axis is the distance away from the interrogation system. Y-axis shows the brilliant frequency in gigahertz. Because the launching fiber and our sensing textile fiber is a little bit different, so you can see the baseline is different. But after point D is where we are installing, we have the launching fiber and also our sensing textile. Figure 7 is the zoom in of this area, and from point A to point B is the region where the sensing textile was fixed on the underneath the bridge using the epoxy. So you can see the frequency change along this area because when apply the epoxy, there are some pre-stress also apply onto the sensing textile. Because this bridge is a functional bridge, we could not conduct this static loading test on it. But this bridge actually is a railway bridge, so there was train passing by every day. So what we did is to monitor the strain distribution when there's no train compared with the signal when the train is passing by. So you can see that this blue and orange color line shows the data when there's no train on it, and the purple and the green color shows when the train is passing by. And figure 9 shows the difference between with train and without the train. So the strain difference is about 87 microstrain. The preliminary result shows that the sensing textile can measure the strain over this distance. And Professor Yu will talk about another approach using the LDV, laser Doppler vibrometer, to collect the data at the same time.
In order to calibrate the measurements collected by sensing textiles, we also use a commercially available laser Doppler vibrometer made by Vibrations Inc. It's a single point digital shortwave infrared laser vibrometer. And this vibrometer has this velocity resolution of 1.7. This LDV has a velocity resolution of 1.7 nanometers per second, displacement resolution of 0.05 picometers, and 1.8 micro G in acceleration. The bandwidth is a 10 megahertz. Measurement distance can be up to more than 300 meters. During our measurements using the LDV, there were two trains passing by the bridge on November 21st, 2019. The LDV was set up from the left support at a distance of 8.9 meters, roughly measuring the midband of vibration. Showing in figure 12 are two strain measurements collected by the LDV. The optical fiber sensor interrogator takes about 3.47 seconds to produce a measurement, In order to compare the sensing textile measurements with an LDV measurements, we had to average the LDV measurements in time. So we used a 3.47-second window to calculate the average strain. And by moving this window, we will be able to calculate the variation of strain during the loading process of two trains. From the moving window calculation, we found that the mean LDV strain measurements was in the range of 34.1 microstrain and 51.4 microstrains. And what about the strain measured by the sensing textiles? If we look at the results in figure 13 and figure 14, we can see that without knowing the actual loads of those two trains, the loading response in train 1 and train 2 resulted in an average strain of 39.9 microstrain. This result can be seen in figure 9 and also figure 14. Now, if we use this mean strain measured by sensing textile and to compare the range, we can see that the sensing textile did produce an acceptable mean strain measurement because it falls within the range of our LDV strain measurements.
After the installation of sensing textile in 2019, we went back to the bridge to collect data in the winter and also in the summer to see if there's any signal change under different temperature conditions. You can see this is the summary in figure 15. In November, December, April, and May, the signal did not change a lot, which means that the sensing textile survived and still working after these 18 months. The biggest difference may happen in the position 1.8 meter and also the 3.8 meter. We find out that, as shown in figure 16, these two locations actually is where the junction of this girder happens. So the reason may be the dry out of the epoxy, which makes the sensing textile not strongly fixed to the underneath of the bridge. So through this project, we have learned how to design different patterns on the sensing textile and also how to fabricate and manufacture the fiber sensing textile with Xingwei. We also learned that the BOTDR could be a practical solution to monitor large-scale structures, as we said that BOTDR could collect data for up to 80 kilometers long. The fiber sensing textile provide reliable signal over 18 months. The data compared between the LDV and sensing textile shows good agreement. Our plan for the coming years, first we will go back to collect data for the long-term monitoring. We want to develop and improve our fiber connection protection kit because that part is the weakest point. We will also further develop the signal processing algorithm to enhance the signal-to-noise ratio. We will also like to try another new integration system to enhance the signal-to-noise ratio as well as to enhance the sampling rate so that we could also monitor dynamic response in the next step. Our team is very thankful for the funding support by TIDC at UMaine. Without this support, this work is impossible. And we'd also like to thank Xingwei for their support in the manufacturing of the sensing textile, and also American Railway engineers for their help in the sensor installation in New Hampshire. This is disclaimer, and thank you very much for your attention.